Download this code from codegive.com, link in the description below. OK, let's dive into a significant security vulnerability that affected the libvpx library, a widely used codec library for encoding and decoding VP8 and VP9 video formats. This tutorial will cover the bug, its impact, how it was exploited, and ways to prevent similar issues. I'll provide code snippets to illustrate concepts, but please understand that running the vulnerable code examples directly is not recommended unless you're in a controlled environment and are conducting security research. Disclaimer *: this information is for educational purposes. I am not responsible for any misuse of this knowledge. Exploiting vulnerabilities on systems without authorization is illegal and unethical. Vulnerability: heap-based buffer overflow in VP9_loop_filter_edges_C. The critical webm bug we're discussing centered on a heap-based buffer overflow located within the VP9_loop_filter_edges_C function of the libvpx library. This vulnerability was widely publicized and assigned CVE identifiers, notably CVE 2018-6156. 1. Background: codecs, libvpx, and video encoding/decoding. Codecs *codecs, coder-decoders, are algorithms used to compress and decompress data, particularly video and audio. Video codecs like VP8 and VP9 reduce the size of video files, making them more suitable for storage and streaming. *libvpx is a reference implementation of the VP8 and VP9 video codecs developed by Google and used extensively across the web. It's used in browsers like Chrome and Firefox, media players, and video conferencing applications. Because libvpx is so widely used, a vulnerability in it has a broad attack surface. VP8 and VP9 *: these are royalty-free video codecs designed for high-quality video transmission over the Internet. VP9 is the successor to VP8 and offers improved compression efficiency. Loop filter * video codecs often use a loop filter as part of the decoding process to reduce artifacts, like blocking, that can appear after compression. The loop filter smooths out edges between blocks of pixels, improving visual quality. The VP9_loop_filter_edges_C function specifically addresses this edge smoothing within the VP9 decoder. 2. The vulnerability: heap-based buffer overflow explained. A heap-based buffer overflow occurs when a program writes data beyond the allocated boundary of a buffer that's stored on the heap, dynamic memory. The heap is a region of memory where programs dynamically allocate space as needed. If data is written past the allocated boundary, it can overwrite adjacent memory, potentially corrupting data structures, function pointers, or even executable code. In VP9_loop_filter_edges_C, the vulnerability arose because the code didn't properly validate the size of the input data or the boundaries within which it was writing. Specifically, the function was designed to filter edges in a video frame, but it didn't correctly check if the loop filtering operation was accessing memory beyond the allocated buffer for the frame. This could happen with specially crafted video files designed to trigger the overflow. Simplified and vulnerable code example, illustrative only, do not run unmodified. Explanation of the vulnerable example *: one video_frame struct * represents a video frame with width, height, and a pointer to the pixel data. 2 process_edge function *: this is a highly simplified version of what a loop filter might do. The critical flaw is that it doesn't check if offset 1, offset +1, and offset +2 are within the bounds of the pixel_data buffer. If offset is close to the beginning or end of the buffer, these accesses will go out of bounds. 3 loop_filter_edges function asterisk iterates through a portion of the frame and calls process_edge for each pixel near an edge. 4 main function asterisk allocates memory for the video frame data using malloc. Asterisk calls loop_filter_edges to process the frame. Asterisk frees the allocated memory using free. Why this is vulnerable asterisk missing bounds checks asterisk the process_edge function directly accesses pixel_data offset 1, pixel_data offset +1, and pixel_data offset +2 without verifying that these indices are within the allocated buffer. Asterisk potential for out-of-bounds write asterisk if offset is a small value, example 0 or 1, pixel_data offset 1 will access memory before the beginning of the allocated buffer, causing a heap buffer overflow. Similarly, if offset is close to frame-width asterisk frame-height, pixel_data offset +1 or pixel_data offset +2 will write past the end of the buffer. Important asterisk this is a simplified illustration. The actual vulnerability in libvpx was far more complex and involved intricate details of the VP9 codec's loop filtering process. 3. Impact and exploitation. Asterisk remote code execution, RCE. The most severe consequence of this vulnerability was the potential for remote code execution. An attacker could craft a malicious webm video file that, when processed by a vulnerable application using libvpx, would trigger the buffer overflow. The attacker could then overwrite memory in a way that allowed them to inject and execute arbitrary code on the victim's machine. This code could be used to install malware, steal sensitive data, or take complete control of the system. Asterisk denial of service, DOS. Even if the attacker couldn't achieve RCE, they could still cause a denial of service attack. By overflowing the buffer, they could crash the application or cause it to become unresponsive. Asterisk information disclosure asterisk in some scenarios, a buffer overflow might allow an attacker to read data from memory locations that they shouldn't have access to, potentially revealing sensitive information. Exploitation steps, general overview. 1. Vulnerability identification asterisk discovering the vulnerability through fuzzing, code analysis, or security research. Fuzzing involves feeding a program a large number of malformed inputs and observing if it crashes or exhibits unexpected behavior. 2. Exploit development asterisk crafting a malicious webm video file that exploits the buffer overflow in vp9_loop_filter_edges_c. This requires understanding the memory layout of the libvpx library and the target application. Determining the exact offset and size of the overflow. Crafting the overflow data to overwrite a function pointer or other critical data structure with the attacker's desired code address. 3. Payload delivery the malicious video file is delivered to the victim. This could be through embedding the video in a website. Sending the video as an attachment in an email. Tricking the user into opening the video using a vulnerable media player. 4. Code execution when the vulnerable application processes the video, the buffer overflow is triggered, overwriting memory and allowing the attacker's code to execute. Simplified example of a conceptual exploit. Do not run directly. Explanation of the conceptual exploit 1. Buffer allocation allocates a buffer of a specific size. 2. Payload creation creates a payload. In a real exploit, this would be carefully crafted shell code, machine code, designed to execute the attacker's commands. In this example, it's just a string of A characters for simplicity. 3. Offset calculation determines the offset within the buffer where the overflow will start. A real exploit would require careful calculation of this offset to overwrite a specific memory location, such as a function pointer. For mempb overflow * simulates the buffer overflow by copying the payload into the buffer starting at the calculated offset. This overwrites memory beyond the allocated size of the buffer. Why this is dangerous, and why you shouldn't run it directly. Memory corruption * the overflow corrupts memory beyond the allocated buffer. This can lead to unpredictable behavior, including crashes, data corruption, and potentially allowing the attacker to execute arbitrary code. Security risk * A real exploit would use carefully crafted shell code to gain control of the system. This code could be used to install malware, steal sensitive data, or take complete control of the system. 4. Mitigation and prevention. Patching * The most important step is to apply the security patches released by Google and other vendors that address the vulnerability. These patches contain fixes to the vp9-loop-filter-edges-C function and other related code to prevent the buffer overflow. Make sure you're using the latest version of libvpx, and any applications that use it. Bounds checking * Implement robust bounds checking in your code. Before writing to a buffer, always verify that the index is within the valid range. Use functions like strncpy or tinprint to limit the number of bytes written to a buffer. Fuzzing * Use fuzzing tools to automatically test your code for vulnerabilities. Fuzzing involves feeding the program a large number of malformed inputs and observing if it crashes or exhibits unexpected behavior. This can help identify buffer overflows and other memory corruption issues. Address space layout randomization ASLR randomizes the memory addresses of key data structures and executable code. This makes it more difficult for attackers to predict the location of these objects and execute arbitrary code. Data execution prevention DEP prevents code from being executed from certain memory regions, such as the stack or the heap. This makes it more difficult for attackers to inject and execute shellcode. Compiler-based protections * Modern compilers often provide built-in security features, such as stack canaries, which can help detect buffer overflows on the stack. Enable these features when compiling your code. Code reviews * Conduct thorough code reviews to identify potential vulnerabilities. Have experienced developers review your code and look for common security pitfalls, such as missing bounds checks, unchecked return values, and insecure function calls. Use safer memory management techniques * Consider using safer memory management techniques, such as smart pointers or garbage collection, which can help prevent memory leaks and dangling pointers. Static analysis tools Static analysis tools can automatically scan your code for potential vulnerabilities without running it. These tools can identify common security issues, such as buffer overflows, format string vulnerabilities, and SQL injection vulnerabilities. Web application firewalls WAFs For web applications, consider using a web application firewall WAF, to filter out malicious requests that could exploit vulnerabilities in your code. Example of safe bounds checking, illustrative. Explanation of the safe code *. Explicit bounds checking * The safe_process_edge function explicitly checks if the offset 1, offset +1, offset +2 indices are within the valid bounds of the pixel_data buffer before accessing them. Error handling * If any of the indices are out of bounds, the function prints an error message and skips processing that pixel. A more robust error handling mechanism could be implemented, such as logging the error or returning an error code. Key takeaways *. Asterisk buffer overflows are a serious security vulnerability that can lead to remote code execution, denial of service, and information disclosure. Asterisk the libvpx vulnerability highlights the importance of careful bounds checking and secure coding practices. Asterisk always apply security patches and use mitigation techniques such as ASLR and DEP to protect your systems. Asterisk use static analysis tools and code reviews to identify potential vulnerabilities in your code. Asterisk be extremely cautious when handling untrusted input data, such as video files. Validate the input and sanitize it before processing it. This comprehensive explanation should provide a strong understanding of the libvpx vulnerability, its impact, and how to prevent similar issues in your own code. Remember to always prioritize security and follow best practices for secure coding.